Today we're going to learn about the 2, 3, 4 tree. Hello, I'm James Helfrich. The binary search tree only retains its desirable performance characteristics if the left side and the right side are roughly the same height. But how do you keep a tree balanced so the left side and right side are roughly the same? Well, one of the methods is the red-black tree. But how does a red-black tree work? Well, we're going to learn about that by first learning about the 2, 3, 4 tree, and then we're going to see how the 2, 3, 4 tree relates to the red-black tree. The binary search tree is not a 2, 3, 4 tree. However, they behave the same, and the 2, 3, 4 tree is easy to understand. So each node of a 2, 3, 4 tree can have up to 3 values, each arranged from smallest to largest. This is an example of a 2, 3, 4 tree. The 2, 3, 4 tree has a additional property of being a complete tree. This means the path from the leaf to the root is always about the same length. Notice how the 2, 3, 4 tree is roughly balanced. Since the tree must be complete, the most lopsided tree would be is when all the nodes on one side have 3 values, while all the nodes on the other only have 1. So what are the rules for a 2, 3, 4 tree? First, every node in a 2, 3, 4 tree must have 1, 2, or 3 values. Second, each value in the node is arranged from the smallest to largest. And third, the subtree under the leftmost pointer of a given node contains only values less than or equal to the first value in the node. And this is similar to the binary search tree's less than constraint. Next, a subtree under the next pointer is greater than or equal to the first value of the node, but less than or equal to the next value of the node. In other words, take a look at the node that has 06 and 10. All the nodes to the left of 06 must be smaller than 06 or equal to. All the nodes between 06 and 10 must be between the two, and 8 is. And everything that's to the right of 10 must be greater than 10, and 12 and 14 are. And finally, values are added to the bottom of the tree. When a node is full, then the parent node is split. And we'll see how that works in a second. Okay, so let's take a look at some splitting. Which of the nodes can accept a new value without splitting? Well, 50 can. In fact, there could be 3 values there and it only has 1. 11 and 26 can. It can accept 1 value. 67 can accept 2 values. 3 and 9 can accept 1. 12 can accept 2. 28 and 38 can accept 1, but this node cannot because it has 3 values, and this node can accept 1 value. So therefore, all the nodes but the node called 52, 55, and 61 can accept new values without splitting. Consider the following 2, 3, 4 trees. What happens when you add, well, 19 to the left tree? Well, 19 is less than 50, so I go left. 19 is between 11 and 26 going down the middle, so I'm going to add 19 right next to 12. What happens when I add 64? Well, 64 is greater than 50, so I go right. It's less than 67, so I go left. So I need to put it in the 52, 55, and 61 node. Well, I can't because it's full. So therefore, I got to split that node into 2. So 55 will go up to join 67, and then I will add 64. I'm going to insert the following nodes into a 2, 3, 4 tree. First 80, and since 80 is the first node, then it's going to be by itself. Then 70. 70 is less than 80, so it goes to the left of it. And then 60. 60 is smaller than 70, so it goes to the left of it. Now I like to add 50, but this node is full. This requires me to split the node, so 70 will go up, and 60 and 80 will remain. And then I will add 50 to the left of 60. Now I'll add 40. 40 is smaller than 70, so I go left, and it's smaller than 50, so it joins that node. Then I'll add 30. Well, 30 is less than 70, so it goes to the left. And I cannot add it to the 40, 50, 60 node because that's already full. So I'm going to split that node, so 50 will go up, and now 40, 60, and 80 will be the leaf nodes, and now I can add 30. Now I'll add 20, and there's room to the left of 30 for that, no problem. Then I'll add 10. Now, once again, 10 is less than 50, so I go to the left of 50, and the 20, 30, 40 is already full, so that means that 30 is going to go up and join 50 and 70, and that means I'm going to have 4 children, 20, 40, 60, and 80, and then I'll add 10 to the left of 20. Let's do a more complicated problem. I'm going to add 50, it's by itself. I'm going to add 40, it goes to the left. I'm going to add 80, it goes to the right. Now I'm going to add 10. Now my node is full, so I have to split it. So it means 50 is going to come up, 40 and 80 be next to each other, and then I'll add 10. I'll add 20 and 70 and 90. and now my two leaf nodes are full. I'll add 60. Now, 60 is greater than 50, so I go right. And now 70, 80, 90 is full, so I have to bring 80 up. And then I can add 60 besides 70. Now I'll add 30. Now 30 is less than 50, so I go left. And now 20, 10, 20, 40 is full, so that means 20 will have to go up, so I will split it. Now, after I split, observe that 10 is less than 20, 40 is between 20 and 50, 60 and 70 are both between 50 and 80, and 90 is greater than 80. All right, now I have to add that 30. Now, 30 is between 20 and 50, so I go down the middle, and it goes to the left of 40. Now I'll add 100 and 110. And then when I add 120, I have to split again. So I'm going to have to move 100 up to the root node. But that's full. So at first I have to split the root node. So the root node will go 50 on top, and then 20 and 80. Do that again. So remember, now 20 has 10 on the left side and 30 and 40 on the right side. And then 80 has 60, 70 on the left side and 90, 100, 110 on the right side. And it still does here. The only thing is I'm moving 50 up. Now that I'm finished with that, then I can move 100 up next to 80 by splitting it. Now, once again, 90 is going to be to the right of 80. 90 will be to the left of 100. And 110 will remain to the right of 100. And now I can finally add 120. I bet you're asking, how do we turn this 2, 3, 4 tree into code? Well, it seems very complicated, and it is. So we're going to do something simpler. We're going to turn it into a binary tree with have special colored edges. Now, my black edges are going to be between 2, 3, 4 nodes, and my red edges will be between them. Okay? So let's see how this works. I'm going to take that same 2, 3, 4 tree, and now I'm going to expand it a little bit. And notice that gray outline is the 2, 3, 4 nodes. The black edges go between the 2, 3, 4 nodes, and the red edges go in between, go inside a 2, 3, 4 edge. And then that actually becomes a 2, 3, 4 tree where the nodes themselves are colored. So 16 is going to be black. 10 and 24 will be black. And then 12, 20, 26, 4, and 8 will be black as well. Now, one of the rules is every 2, 3, 4 node has exactly one red black node. And then if there is more than one 2, 3, 4 node, then there's going to be a red node in the red black tree corresponding to it. Okay, let's see how that works. On the left here, I have a 2, 3, 4 tree. And if a node is, and there must be at least one black node for every 2, 3, 4 tree, and the other ones must be red. And since we have an additional rule that red nodes can't be next to each other, so I'm just going to color that 2, 3, 4. And now the red nodes are below the black ones, so that becomes this. Now on the tree on the right here, every 2, 3, 4 node must have a black node. And since all these nodes only have one, they're all black. And therefore, this is just a straight red-black tree. Okay, so now I have a red-black tree, and how do I turn it into a 2, 3, 4 tree? Well, first of all, this guy right here is going to be a 2, 3, 4 node. And the reason why is because every 2, 3, 4 node must have one red-black node. This will be 1, this will be 1, and this will be 1. So when I flatten it out, we'll see the root node is 40, 70. To the left of 40 would be the 20 with a 10 and 30 on one side. To the left of the 70 will be the 50, 60, and to the right of the 70 will be the 80. And that's my 2, 3, 4 tree. Note there are exactly 2 black nodes between every leaf and root. This means the height of the 2, 3, 4 tree must be 2. We can learn more about the 2, 3, 4 tree and how it relates to the red-black tree in the binary search tree chapter of the C++ data structures textbook.